When discussing quantum physics, the most fundamental, most important, and most crucial piece of information is this. Light behaves both as a particle and as a wave. This information forms the cornerstone of what we need to know about quantum physics. The dual nature of light explains why quantum physics goes beyond traditional understandings of physics and why it must be approached from a different perspective. Quantum physics is built upon this dual nature, and all our knowledge has developed from this understanding. This information is like a key that opens the doors to an incredible universe we discovered while trying to make a light bulb more efficient. And you know what happened next. A whole new physics, a whole new mathematics, a whole new understanding. A world where certainty is replaced by probabilities, randomness, and uncertainties. This uncertainty is perhaps the most important topic we haven't focused on much so far. We've talked about the cat, the double-slit experiment, entanglement. All of these were actually a prelude to this video, because they all rest on a principle we haven't yet discussed in detail. The uncertainty principle. Heisenberg's uncertainty principle. In 1926, while trying to make sense of this new universe, Werner Heisenberg began developing a theory based on wave mechanics. He used equations that had never been encountered before. While working with Niels Bohr in Copenhagen, he discovered something interesting when trying to measure a particle's position and speed simultaneously. You could either measure its speed exactly or its position. No matter what you did, you couldn't measure both a particle's speed and position at the same time. At this point, we might immediately think of the observer or the measuring device interfering in the situation. In the double-slit experiment, this was the only solution, wasn't it? However, Heisenberg's groundbreaking conclusion in physics was this. This situation, the inability to measure both properties at the same time, was a fundamental phenomenon of the subatomic world. When Heisenberg expressed this, he instantly became the leader of the quantum revolution. While everyone was searching for an answer, this lack of an answer, this claim of an uncertainty principle, caused all scientists to stop their work and listen to Heisenberg, a genius at just 26. Because before Heisenberg, everyone still had a bit of hope. All the scientists were sure that someone would find an explanation for these absurdities. But Heisenberg said, there's no need to search, because now quantum physics was telling us it's impossible to know a particle's exact speed and exact position at the same time. Because what we call a particle is not just a particle, but also a wave. The speed we talk about here is actually momentum. But the concepts are quite close, so I will continue with speed and position to create the necessary image in everyone's mind. The issue is much deeper here. At this point, we might ask, okay, we understand that we cannot know both a particle's speed and position simultaneously. But why is this important? This information is crucial because it is one of the most important foundations on which classical physics is built. Think of classical physics as an arch, the keystone at the top. If you remove it, the arch cannot stand. This is a simple way to explain where classical physics gives in. So, what is this uncertainty principle? What are we talking about? Before diving deeper, let's make the topic a bit more interesting. Let's go back a few years before Heisenberg proposed his theory to 1923 and talk about de Broglie. De Broglie is one of the key figures in this story, and de Broglie had a belief. He believed there must be a parallelism in nature. That's why he searched for a parallel in the wave-particle duality of light. The issue of light being both a particle and a wave. We kept talking about photons, massless particles, intangible. He asked, what about particles with mass? Larger objects, even us. Shouldn't there be uncertainty in them as well? Because that's how nature worked. All objects must have a wave property. And de Broglie was right. We would see this again in the double-slit experiment. When we started firing electrons instead of photons, a wave pattern still emerged. This showed that atoms, molecules, everything must have a wavelength. Yes, we also have a wavelength. It's hard to grasp, but everything around us has a wavelength. We calculate this using the formula. Wavelength is found by dividing the Planck constant by momentum. But you know the Planck constant, a very, very small number. So, as momentum increases, the wavelength naturally equals an incredibly small number. For example, if we try to calculate the wavelength of a 200-gram baseball sliding at 40 meters per second, we get such a number. This actually explains why we can't see or measure this wavelength. But now, we know that everything has a wavelength. Therefore, everything with a wavelength, everything that behaves like a wave, also floats in a sea of probabilities. But to fully grasp the topic, let's return to the particles we can measure: electrons, atoms. If we look at the double-slit experiment again, we can see the explanation for why electrons form a wave pattern. If we consider the equation we applied for the baseball, the smaller the particle, the larger the wavelength will naturally be. It behaves more like a wave. The more a particle behaves like a wave, the greater the uncertainty naturally becomes. That's why, in the quantum world, there's a probability of something being somewhere. In classical physics, you can't know exactly where it is. Only probabilities. Everything is filled with probabilities. Nothing is certain. I know this is confusing. It seems like everything is unraveling, doesn't it? But this is how the universe works. This is our mechanism. You, me, everything. Probabilities. So, does this mean we can't know anything precisely? Of course not. We can make very close estimates, thanks to Erwin Schrödinger. Schrödinger, known for his cat, showed us how to calculate this quantum probability, the wave function of particles. This seemingly complex equation actually tells us where we are most likely to find a particle. We call this the probability density function. At this point, we also need to briefly mention the atom model. The atom model developed by Niels Bohr looked roughly like this. However, with the uncertainty principle, this model transformed into this. Because no matter what we did, we couldn't find out exactly where the electron was around the nucleus. In the new atom model, these cloud-like formations around the nucleus represent the regions where the electron could be. Schrödinger's equation allows us to make this calculation. But this is where the most serious debates about quantum physics begin. One of the most confusing topics is this. Now, there's a situation where we know the position of particles when we measure them, but we don't know where they were before measuring. When we measure them, we think they are there, as if we've caught a fly in flight when we measure it. However, actually, when we measure, the electron in the probability cloud we mentioned is everywhere. At that moment, the particle is actually everywhere. We only narrow down the probability when we measure. We don't learn its position. By measuring, we force it to be in a specific place. We called this quantum superposition. The probability of a particle being in multiple states simultaneously. Schrödinger tried to explain this to us with his cat. It's a really useful metaphor, but people might miss the essence of the topic. However, of course, things don't stop here. It gets even more complicated. This is where Heisenberg comes in. We measured the electron that was everywhere at once and forced it to be in a specific place, right? Heisenberg says, you measured it, but this measurement is not exact. Yes, Heisenberg's uncertainty principle. As I mentioned before, Heisenberg tells us with this principle, no matter how good or precise your measuring device is, you can only know a particle's, an electron's position or speed to a certain extent. If you want precise information about the position, you cannot know its momentum exactly. The same goes the other way. You have to make a sacrifice. It's impossible. Why? Again, it's related to the wave-particle relationship of matter. As I mentioned earlier, the speed or momentum of a wave is found by dividing the Planck constant by the wavelength. But when you use this, you're considering the wave property of the electron. Yes, this way you can know its momentum Exactly. But when you consider something as a wave, you also accept that it is spread everywhere. That's why it's impossible to know its exact position. You say, okay, let's consider the electron as a particle. This time, you learn its exact position, but to find its momentum, you need to make two measurements and calculate the elapsed time. However, since you sent a photon to the particle in the first measurement, and this photon's momentum also passed to the particle, you cannot reach a definitive conclusion between the two measurements. In summary, it's impossible to measure both a particle's position and speed and obtain exact information at the same time. And this is very, very different from our classical perspective, from the way we experience the world. But as I said, this is the best explanation of reality. Everything in the universe floats in a sea of probabilities. Nothing is certain. And everything is made up of these uncertain, unfathomable, very, very small particles. They came together. They will come together. From the smallest to the largest. A whole of particles we cannot understand. And in this journey, as we have talked about before, there is an invisible bond between these particles. These seemingly meaningless building blocks form an almost perfectly functioning order. At least we think so. We want it to be so. Because as you will see in the following videos of this series, in the quantum universe, there is chaos. Chaos with its own order. What we are trying to do is find these connections. As I always say, we are actually in the midst of one of the most important and exciting discoveries in history. We have summarized the basic topics we need to know about quantum physics in the simplest way. Now we will accelerate towards the present and beyond, and we share this excitement together. That's what makes me happiest. The quantum adventure continues at full speed. Stay tuned. Before I finish, I try to follow scientific developments and make constant posts on Instagram and Twitter on non-video days. I hope we meet on these platforms too. And as always, until we meet again. Glad you're here. Best wishes.